Hello, today I want to talk briefly about Fermat's theorem. Fermat's theorem just says that if a differentiable function has a max or a min at a point, then its derivative must be zero, if your function is differentiable. Right? So the picture that goes with this is I think makes the theorem somewhat intuitive. Imagine the graph of a function. And on this function, I'm going to look for a point where there's a max. I'm going to look for a point where there's a min. And I want to ask, what is the slope of the tangent line at each of those places? Well, you can imagine that over here, the slope was positive, right? I had positive slope. I was climbing uphill, positive slope, right? Until eventually it leveled off and then started going back downhill again, right? Well, that place where it leveled off, we don't really need these other slopes. That place where it leveled off, that's exactly the max, right? So this is slope 0 at the max, right? A horizontal tangent line. Similarly, now we go downhill, downhill, downhill. We have negative slope tangent lines until we get to this min, and then this would have slope 0, right? The tangent line is again horizontal at the min, right? So that's the kind of the picture that accompanies this theorem. Horizontal tangent line. You would definitely have a horizontal tangent line at a max or a min, right? And now I want to, I'm not going to prove this formally, right? There's a proof of this in the textbook, in my textbook. So that's I think a great place to read that. Obviously I'm biased, but I would recommend that right up. But what I do want to do is just demonstrate this in an example, right? So for example, suppose we have a parabola, right? A classic graph from we studied all the time back in, say, in college algebra, right? And let's say we have a parabola x squared minus x plus 3, right? Suppose this is our parabola. So here we can actually, we have a formula for this, right? We can find the vertex of this parabola by completing the square, right? This is a technique from college algebra, from pre-calculus, right? So I can put this parabola in a different form. So I can say, okay, this is x squared minus x plus 1/4 minus 1/4 plus 3. And where did the 1/4 come from, right? What's the trick when you complete the square? Well, you take the linear term, sorry, the linear coefficient, which here is -1, right? You cut it in half and you square it, which equals 1/4. And that's the quantity that then you add and subtract, right? So half of the linear coefficient squared gives you what you add and subtract. And then this trinomial, this initial trinomial, becomes a perfect square. And then the other constants you can just combine, right? So this is 11/4. Right? So there we go. There's our parabola in vertex form. And once you see it in vertex form, then we can graph it very easily, right? So we say, okay, this graph now is, here's x, here's y, and this graph looks like what? It looks like a standard. Think of transformations, right? Think of a standard parabola, y equals x squared, but it got shifted to the right by half a unit, and then up 11/4, right, is how we would translate this. So we want to move this graph to the right and up, right, and we would get a new graph that looks like this, right? So if we want to show that on its own axes, right, we don't need the parent graph anymore, right? This is, right, so this is the 0.1/2 comma 11/4, and then we draw a parabola from there, right? So there's our graph of our function f of x, right? Which f of x equals x squared minus x plus 3. So there's our graph, right? Now, what is this vertex of the parabola. This vertex is a min, right? This is, and in fact, this is the absolute min of the whole graph, right? It's not only a min locally, but globally. So what does Fermat's theorem claim? Because I have a min, it claims that I should have slope 0, right? By Fermat's theorem, I should have a horizontal tangent line. So let's check this claim of Fermat's theorem, right? Let's observe to see if this is actually true. So let's check, right? Fermat's theorem claims that f must have a horizontal tangent at 1/2 because what? It's a differentiable function that has a min at that point, right? Polynomials are differentiable everywhere. It's differentiable and it has a min, right? So let's check this now. So how can I check this? Well, take the derivative, calculate, right? Do the derivative of this function, right? So I get what? I can apply linearity and power rule, right? And I get 2x minus 1 as the derivative. And now I can plug x equals 1/2 into that formula. You know, you could use limit definition of a derivative here, but we don't really need to. We have these nice properties, power rule, linearity. So I'm using the slick tricks, right? So this is 2 times 1/2 minus 1 gives 1 minus 1, which is 0, right? There we go. There, we verified Fermat's theorem, right? The function had a min at x equals 1/2, and sure enough, the derivative was 0, just like Fermat's theorem promised. So this is our little example demonstrating the validity of Fermat's theorem in this one case. Right? So hopefully that's an example that illustrates the theorem nicely. One thing that I want to mention is this does not necessarily go the other way, right? The converse is not true, right? It is not the case that this is a warning, right? This is maybe something good to write in red or something, right? So warning, the converse is not true. Classic example here is you could have, right? You can have a function who has derivative 0, but does not have a max or a min, right? So these points are called saddles, right? So saddles exist. And the classic example of a saddle is the function f of x equals x cubed, right? Actually has derivative 0, right? It has a horizontal tangent line at the origin, but no max or min, right? I can check that it has derivative 0, right? Take that derivative, f prime is 3x squared, and then f prime of 0 is 0 because it's 3 times 0 squared, which is 0. So yes, it has a horizontal tangent line, but no max or min. Why does it have no max or min? Well, this graph is increasing everywhere, right? X cubed goes up, it levels off, and it keeps going up, right? So that's why it has this horizontal tangent, because at the origin, it's actually completely level, right? It has slope 0. So it's uphill, and then it plateaus at the origin, and then keeps going uphill again, right? So that's it doesn't go uphill, plateau, and then come back down. Right? It just goes uphill, plateau, and then keeps going up. So that's an example of a function that does have derivative 0, but no max or min, right? So you cannot necessarily conclude that a function has a max or min at a point just because the derivative is 0. But the other way around, yes. If a differentiable function has a max or min, then definitely the derivative is 0 at that point. So there we go. There are some examples surrounding the key idea of Fermat's theorem. Thanks.